Okay, guys, so for number 6, this is the idea. Okay, so what do I mean by the two random notions? So you could first have the identities of the objects that you are grabbing, that you're sampling, defined. They are already precise, and then the sampling is random. Or you could take the sampling not at random, but then as soon as the sampling is done, those objects are transformed. That's why I mean this statement: you cannot grab your dream in your hands. Нельзя мечту свою хватать руками. Because there is this line: когда коснемся мы, когда прозрачно, I lose the phrase since it's in the middle. Когда, пленясь прозрачностью медузы, ее коснемся мы капризом рук, она как пленник, заточенный в узы, вдруг побледнеет и погибнет вдруг. Which means when enthralled by the transparentness of a medusa, we touch her with our capricious hands. Like a prisoner in chains, it will suddenly become pale and die. Do you understand? So that means that I understand it probabilistically as saying what? As saying that once you hold the object, once you sample the object non-randomly, suddenly its transformation might be random. That's why I remember this quote. Do you understand what I mean? And that's what this question is really about. Question number 6. Do you follow? Right. So
Professor?
capture Ricard. Yes.
Professor, I think Marina Tsvetaeva is a little tragic to quote. Her life was very sad.
Yes. Well, our lives are going to be very sad. Soon you will be all quoting Marina Tsvetaeva. You know what's good about suffering? What's good about suffering?
No, nothing good. No.
Is that it builds the soul, right? It builds the soul, and it makes your inner world beautiful. So you might have a beautiful outer world or a beautiful inner world. And as things are becoming worse, as there is going to be there's already a lockdown in Germany, again, another one, right? And there's going to be one here, and other consequences. And soon you will be quoting and of course censorship is on the rise. So soon you will be quoting Tsvetaeva or the equivalent, maybe in English. So back, and by the way, nice to see you. Some of you I see for the very first time. Isn't it impressive, right? My God, hello. Who are you, strangers?
There's amazing things people do for extra credit.
Yes, by the way, here is another extra credit possibility so you don't feel so terrible about exam 1. We need to figure out, oh my God, ooh, I never had so many people in class. So impressive. Another thing is, of course, I wonder what sort of, I'm going to try next semester to force everybody, flush them out. Although of a libertarian nature, I do not like to force people. You see, it bothers me. I want them to do it out of their free will, so to speak, even though I don't believe in free will. So you just have to tell me, of course, maybe you have some suggestions of how can I entice you to have done that more before. Right, so you see, most of you were not showing me your faces, and it makes me wonder if it's extra credit or some other things. I'll try to figure out how do I make people show me their faces, so I know who I talk to. Okay, so this question, do you understand it, guys? Do you understand question number 6 or not yet?
I understand part A.
Okay.
I don't really get part B.
Well,
like, so
again, you see, is there a difference? You see, what sort of objects are we dealing with here? I don't remember their names, right? But you basically imagine you have blue and red balls, right? And what you can imagine is you're going to sample some balls randomly, and then you ask, what's the probability you sampled k red balls, right? You have a certain number of blue balls, certain number of red balls, right? So usually what you think about is that the sampling, the balls that you grab in the urn, like when you play the game, the balls that you pull out of the urn are pulled out randomly. Agreed? They are pulled out randomly, but their color was determined before they entered the urn. right? I'm asking you, is there any difference, speaking probabilistically, from this effect to the effect that you pull a ball without randomness? You look at them and they are entirely without color. And once you selected your sample, because if they're exactly the same, you select first that you see, second, third, fourth, and then as soon as you select them, all the balls, the ones in your hand and the ones that are not in your hand, transforming like the medusa, changing color, becoming red or blue balls, but randomly, with exactly a certain number becoming red and the other becoming blue. Do you follow? Imagine you have 5 blue, 5 red balls initially, and you ask what's the probability of randomly sampling 3 red balls out of a sample of 7 or something like that, right? Do you understand? So I can imagine this, the balls already colored, definite, and my sampling random, or I can imagine my sampling being non-random and then the color assignment is suddenly random. Is there any difference probabilistically? That's the question. Do you understand? That's the same thing. I just had to place it in a way that will maybe elicit some reaction from you. Maybe. Right? This, by the way, question number 2, it's true. You see, so this was, oh no, it is in final. You haven't even seen the final. I forgot. I'm very proud of question number 2 on the final. Or not proud. I mean, it has to do with my cousin, a very foreign entity. All right. After, can we go over 4? So here's question number 4. Is this the question 4? Yeah. Jimmy buys N Wonka chocolate bars, 2 of which contain a golden ticket. The wrappings are opened randomly without replacement. Let X be the number of Wonka bars opened until all the T golden tickets are found. Okay. Find the probability mass function of X and compute the expected value of X. Do you understand what are Wonka bars? This is something that you should know better than me. I never eat American chocolate. It tastes like butter. So what do I mean? We have N chocolate bars. 2 of them contain tickets. They look identical. So I open the first, second, third, fourth, all the way until I reach the T, right? X be the number that I have to open. I don't continue opening once I already had the tickets. I don't want the chocolate. I want the tickets. Usually I think you want 1 ticket, but that doesn't matter. You understand the problem. You want to gather all the tickets, 2 of them. Good. What does the problem remind you of? For problem number 4 should remind you of something from exam 1. Do you agree? No? The transistors. It's the same thing really, right? What's the difference here? It's the same thing. I need to find the broken transistors. Here I am finding Wonka bars, so Wonka tickets, whatever. Yes? Clear? Oh, goodness. Not all of you look happy. Maybe that's why you don't like to show me your face. Or some of you know that you cheated on the exam, right? And then I see it in your eyes. Yes. Okay. So, what other things may I help you with before I move on with today's lecture? 7. So what I'm saying helps you, right, guys? I mean, you're getting inspirations on this exam. 7. Oh, 7 is a hard problem. This is hard. So see, so don't worry if it's too hard. But yes. So you see, it's a bit. So you play a game in which you may roll the die once, twice, or 3 times. You understand? So you can decide at any moment how much to roll. Good. So if you see, what you're gonna get is the payment for your last roll. You understand? You can get either 1 or 2 or 3 or all the way to $6. So tell me, if you roll a 6 on the first trial, would you roll again? No. Because you can only get 6 or less. Why would you want to get less? Of course, maybe you're a humanitarian, really like to give your money to charity, right? So maybe because of that, you want to gain less. But if your goal is to get the biggest number and stick with it, the biggest payoff for the game, once you roll a 6, you don't move onwards. Do you agree? Now tell me, if you rolled 1, would you roll again? Of course, because you rolled 1, well, you either gain 1 or something more. You don't lose anything if you roll again. Do you agree? So far, good? So do you agree that your decision for this game, no matter how many rounds I play, should always be based on the previous round? Because you cannot go back to first, second. You see, if you played 5 rounds of this game, you decided to play, when you decide to play the 6 or not, it's already because the die is fair. You understand? The die is fair. So whatever past numbers you receive, they don't influence your score. Your score is always the very last roll. You either stop now and you get whatever price was the last roll, or you continue playing. Do you follow? So do you see? That's why it's the game. So you need to understand what happens on 2 rolls. What's your strategy with 2 rolls? Because at any moment you only consider the previous roll. Do you agree? You understand why I don't need to consider all the dice. If I were to play this game not 3 times, but if I were to play it 10 times, only the 9th time, when I make a decision to play it for the 10th time or not, I only have to look at the outcome on the 9th trial. Do you agree? If I understand what's the strategy on 2 trials, then I understand what's the strategy for any number of trials. Do you follow what I'm saying, guys? You see how I reason? Because you can decide whether to stick with what you have or to go again. And to stick with what you have is what happened right now, or to play another round. You follow? So your decision is always made based on the previous round. And then you're in a new situation, and then based on the outcome of that last round, you make the next decision. But your decision does not have to refer to previous decision made. You follow? So then you already have some strategy. You all agree that if you rolled 1, if whatever number of trials, if let's say, forget where I am, I spaced out, and I am in some new round, right? Let's say maybe I played 25 rounds of this game. Here you're only allowed to play 3. But suppose I played 25 rounds, and then I wake up and I wonder, do I want to play again? And I look at the die. If the die shows 1, then I want to play again. If the die shows 6, then obviously I don't want to play again, right? But what should be the situation? Otherwise, I don't want to throw the next round. I don't want to cast the die. But what should be exactly the strategy? So investigate it for the maximum expected value. You see, what should be your strategy to get the maximum? Yes, so you should know what to do when you get 2. What do you do? If let's say you roll it for the first time and it came out 2, should you roll again or should you stay? If you roll 3, should you roll again or should you stay? And what you do is you try to maximize your expected value, right? If you were to play such game many times, what's the best decision? You follow? Yes, guys?
Oh, Professor?
Yes.
So it says the choice whether to roll again or not is... Oh, never mind. I misread that.
Yes, you can make the choice. You understand? You don't have every round. You can decide to stop or play again. Clear? You decide whether you roll again or stop.
So, like, if I figure out, like, the best strategy for roll number 3, then that strategy is also applied to 1 and 2, right? Because 1 and 2 don't influence 3.
Yeah, so it's only your strategy is always based on the previous roll. That's why for this game you only need to consider only two times when you roll the die, when you're allowed to roll it twice. You understand? Because if I understand what should I do when I am allowed to roll it twice, I understand what I should do no matter how many times I'm allowed to roll.
Oh, so
for example, suppose I'm allowed to roll 7 times. So let's make it 4 times, right? And let's say first outcome was 1. Do you roll again?
yeah.
And then suddenly next outcome was 1. Do you roll again? Yes, right? Why do you make the decision? You forgot that the previous outcome was 1. You see, now it's 1, then therefore I roll again, right? If it's again going to be 1, you roll again. Do you understand? And suddenly, let's say on the third trial is 6. Do you roll again?
I mean, you can't.
You can, but do you do it?
No.
You are allowed to do it, but do you do it? You see, you don't do it. Do you understand why you don't do it? Because you can only lose. You roll it again, you will not gain anything, you can only lose. So you know clearly what will happen if you do it with 1 and 6, but you don't know what would happen. What should your strategy be if it's 2 or 3 or 4 or 5? So you have to decide based on one time. What decision is when the game begins. Based on that outcome, decide what to do next. Roll again or not roll again. You have decision to roll again or not roll again. That's the only thing in your control. Do you follow? And your goal is to create a decision scheme to optimize, to make your expected value as big as it can possibly be. It's not an easy question, but I suppose if you'll be interested, also for previous exam, we can go over at some point over the solutions. I don't want to do it today, but we can go over all the solutions. If you see, perhaps we will not part over the winter if you want. If you have, let's say, some things that you're interested in, we can maybe have some problems we solve and we meet to discuss those problems. If you want, we will see if you have the desire to do so. If not, then you are free, of course. By the way, how many would have been interested in such a thing? So the idea is we meet, we discuss, we get some sort of assignment of problems and we discuss how to solve those problems. Would you be interested or you don't really want that? Okay, one person says I do it. Because you guys, you are allowed to have your vacation. I personally, potentially, that's very funny, right? I just have to decide if I will allocate my time for that or not. Very hard problems, naturally, right? That's the point. The point is that we don't really study because we have to get a grade. We study because we want to understand probability, right? And everything else is not material to us. Good? So you'll let me know. Okay, I'll send an email afterwards and we'll see if enough people want it. The idea is you have a collection of problems, just like an exam. And I'm not going to grade it, but we can discuss the solutions together. Okay? Some people I know, they are taking actuarial exams, so we can see if we can include problems from actuarial exams. Stuff like that, okay? We'll see. Anyhow, good? So that's a hard question. I mean, solve others, maybe you can figure it out. It's not too bad. Maybe you can figure it out. But if not, then first do other problems. Good? I will need the exam on Wednesday, I think, right? I said Wednesday the 16th because unfortunately they are truncating my my timeline to grade your scores. I have to submit your grades by the 23rd. Usually I submitted them by January and it took all the time. So that, I just grade and submit it. Good? Onwards, let's begin with exponential variables, yes? Or you will have more questions on that stuff? You don't look happy, you see. I mean, I think I say more problems for everybody, right? Like Santa Claus. But you seem like you are not thrilled by this idea. So what do you would like to, any last questions about this thing or what? No? Okay, then let's go to the lecture. All right, exponential distribution. So a continuous random variable x is said to have the exponential distribution with parameter lambda, where lambda is bigger than 0, if the density function is lambda times e to the minus lambda x. Yes? So the corresponding cumulative distribution just integrated from 0 to whatever value x you get, and that's 1 minus e to the minus lambda x. Good? This is, now we can say that it's sufficient to understand how the distribution is working when the parameter is 1, when lambda is equal to 1, because if y is any other random variable, the probability that y is less than or equal to 1 is the same as the probability that if y, is equal to x over lambda, is the probability that x over lambda is less than y, which is x less than lambda y, integrating, you get that y is exponentially distributed, because here's the density function with parameter lambda. That's not very interesting, so I kind of move fast through it, okay? Okay, so first, expectation and variance of exponential random variables. Good. So clearly I just have to integrate from 0 to infinity x e to the minus x dx. And what do I get? That's integration by parts. Integration by parts means what? Means just we have minus x e to the minus x from 0 to infinity. If you remember your limits, that's just 0, because at infinity, well, e to the minus infinity crushes the x when it goes to infinity, right? So this is 0, and the integral from 0 to infinity of e to the minus x dx, it's 1. So the expected value of exponential with parameter lambda equal to 1 is 1, okay? And the expected value of x squared, carry out again integration by parts, and you get 2, okay? And so variance is also 1. So the expected value and variance of exponential random variable is 1. Good. So what next? So if y is exponentially distributed with parameter lambda, just we know that y is x divided by lambda, and we can clearly adjust. We know expectation of x over lambda is 1 over lambda times x. So the expected value is 1 over lambda, which means the smaller the lambda, the bigger is the expected value. Small lambda makes a big expected value, okay? And the expected value of y squared is 2 times 1 over lambda squared, and so variance is 1 over lambda squared. So the exponential distribution it has a very special property called Memoryless property, which says that if you waited for hours or days or years or centuries and something did not happen, the probability you would have to wait whatever amount of time is not affected by the past, okay? So it's as if it starts from start again. Let me try to show you how that is going to work, okay? Suppose that the time it takes me to grade one of your tests is exponentially distributed with mean of 1 month. Given that you've waited for the results 1 month already, what's the probability that it will take another month or longer to grade the test? You understand? You understand my question? So it's exponentially distributed and the mean is 1 month. So that means that the time is distributed as exponential random variable with parameter lambda equal to 1. So let's consider this calculation. Probability that t is bigger than or equal to 2, given that t is bigger than or equal to 1, right? So that means that you have to wait another month or more, right? T bigger than or equal to 2, given that it's already bigger than or equal to 1. Okay, you see, so that's the probability. I wrote it as 1 plus 1. So here, so it's probability that t is bigger than 2 and t is bigger than 1 divided by probability that t is bigger than or equal to 1. Which of course, it's just the probability of t bigger than 2, given that divided by the probability that t is bigger than 1. Good. Okay, so what do I have here? So I take the integrals, look at it. So it's 1 minus the integral from 0 to 2 of e to the minus x dx divided by the integral from, well, 1 minus the integral from 0 to 1 of e to the minus x dx. Good? And what do I get? I get 1 plus e to the minus x from 0 to 2 and 1 plus e to the x from 0 to 1, which when I simplify, look at it. It's simply e to the minus 1, which happens to be the probability that t is bigger than 1. You understand? So in other words, if the distribution, if it's exponentially distributed, if I said that the way I'm grading exams is exponentially distributed with expected value 1 month, even if you waited a month, it's not going to affect your weight afterwards. Once you already waited a month, it's as if it's starting from start. It's again a brand new situation. It's very strange, right? So this is going to be how we describe the memoryless property. A continuous distribution is said to have the memoryless property if the probability that x is bigger than s plus t, given that x is bigger than s, is just simply the probability that x is bigger than t for all s and t bigger than 0. Do you follow how that works, guys? This is in terms of time. It means the probability you would have to wait additional t units of time, given you already waited s units of time. It's like the probability that you just have to wait t units of time. That's it. The fact that you already waited s units of time is not affecting the probability. Good? Clear? And let's see that any x that has the exponential distribution has that memoryless property. So we're calculating probability that x is bigger than or equal to s plus t, given that x is bigger than or equal to s. Good? So that becomes simply by conditional probability. It's simply the probability that x is bigger than s plus t divided by probability x bigger than s. You understand where x bigger than s disappeared? Because if x is bigger than s plus t, it's naturally already bigger than s. So the intersection is s plus t. Clear? So this just becomes the integral from s plus t of the exponential distribution divided by the integral of s to infinity of the exponential distribution, which once I integrate, you know how to integrate it, right? It's just minus e to the minus lambda x from infinity to s plus t, and here infinity and s on this bounds. And what do I get? Look at it. When I plug in infinity, it's 0. So it's really the same thing as e to the minus lambda s plus t divided by e to the minus lambda s, which is e to the minus lambda t, which is the probability that x is bigger than t. In other words, this is just a calculation that verifies that the exponential distribution has that memoryless property. Good? So if x is a positive continuous random variable with the memoryless property, then x has an exponential distribution. That's the next statement. That's a bit more profound. We're saying now that no other continuous random variables have that memoryless property. If you know that the variable has a memoryless property, then it must be the exponential random variable. Good? Let's see how your faces are, right? How are you holding? All right, so here is how we are going to do that. So if capital F is the cumulative distribution function of this random variable x, we can define capital G. G of x is 1 minus capital F of x. Yes? So that would be probability that x is bigger than little x. That's basically yes, it's the, how do you call it? It's the, I lost the name for it. I think it's the survival. It's what's the probability that x survives to be longer than this little x. Survival rate or something they call it maybe. So by the memoryless property, then we should have that the probability that x is bigger than s plus t, given that x is bigger than s. You see why we want this function? It's because we're considering surviving longer than s plus t, given that we survived longer than s. Right? So we want not the cumulative distribution, but this survival rate function, or whatever it's called. So it's just the probability that x is bigger than s plus t divided by probability that x is bigger than s. And that's supposed to be, because we're assuming this variable has the memoryless property, we're assuming that it must equal to probability that x is bigger than t. You're clear, guys? So in other words, if you survived S, what's the probability of surviving additional T units of time? It's equivalent to just starting the experiment from the beginning and calculating the probability of survival additional T units of time, just from zero, from start. Good? It's a very weird type of distribution. It's very difficult to imagine what might be memoryless. Good? Usually things get older, things fall apart, things react to time. If I survived for whatever years I survived, it's not like I'm a newborn person, right? So what does it mean in terms of our function? Look at it, guys. It means that our function has this property that g of s plus t divided by g of s is equal to g of t. You agree? G of t is the probability that x is bigger than t. And so functionally, we have this, this situation. We have that for all real numbers, g of s plus t is equal to g of s times g of t. Good? You see this line? So in particular, I can try to evaluate what is g of n, sorry, right? So g of n, I can do it by induction. G of n is n minus 1 plus 1. So if I want to, I could label this as my s and this as my t. And so what I should have is I should have g of s, g of t, because this property holds for all numbers, right? So I'm able to separate and write it as gn minus 1 times g of 1. Are you with me? And so I can continue separating it until I have n copies of g of 1. Yes? N copies of g of 1 means it's just g of 1 to the power of n. Now let's try to understand what is g of 1. G of 1 can be written as also as g of 1 over n plus 1 over n times, right? So it's and by this multiplicative property, g of 1 is equal to g of 1 over n to the power of n, which after taking n fruits, I see that g of 1 over n is equal to g of 1 to the power of 1 over n. Yes? And in general, for any rational number m divided by n, positive rational number, let's say, because we're dealing with s and t positive, then we have g of m over n will be simply g of 1 over n added to itself m times, which is g of 1 over n to the power of m, which is g of 1 to the power of 1 over n to the power of m, which is g of 1 to the power of m over n. Now, if you studied analysis, any continuous function is completely determined by its action on rational numbers, right? So I know that all rational numbers can be pushed to the exponent. So g of any rational number is g of the exponent. You follow? So if I say g of r, where r is a rational number, this is g of 1 to the power of r. That's what we established here. Clear? And any continuous function, rational numbers are dense in the number line. So any continuous function has that that is completely determined by its action on rational numbers. If I know what the continuous function is doing to all rational numbers, I know everything about the continuous function. So that means that for any x, g of x must be equal to g of 1 to the power of x. You understand? Because it must match this behavior for all other rational numbers. Have you taken analysis? No? Yes? But not with me, so yes. So I can convert it to exponential, right? Any exponential can be converted to the natural exponential function by this way, right? I can take e to the power of logarithm, right? So if I have, this is what's happening here. If I have a to the power of x, I can also write it as e to the power of ln of a to the power of x, because e to the ln a is just it's just a, and so this is simply e ln a x. Good, which is my I can call it my lambda, so I can say e to the minus lambda, I can call ln a minus lambda times x. That makes it the exponential distribution here. That's what I'm doing next. Clear? You see, that's what I do. I say g of x is equal to e ln of g of 1 times x. And g of 1 is, I can write it as, I can push the minus, it's e to the power of minus ln of 1 over g of 1 times x. So, so my random variable, it becomes g of x equal to e to the minus x here, okay? This way I can make it look like this situation. Good? So here I have my exponential random variable where, yes. So that shows us that x is actually, it has this distribution. So I found this function as my survival rate function, and therefore the cumulative distribution is 1 minus this function. And so when I take the derivative, I get that f of x is equal to lambda e to the minus lambda x. Good. So I show that this is, it has the exponential distribution for the appropriate lambda. So that those are the only continuous random variables with yes, and this is, you see, yet another desire to be to quote a poem. I always have it. I cannot avoid it, I guess. So it is very difficult to imagine that there is anything in nature that is truly memoryless. As Alexander Gradinsky sings, nothing on earth passes without a trace, and bygone youth is nonetheless immortal. If you want to hear the song, I can play it for you, or at least I can play you that line. Do you know it, Valeria? No? No, окей. Ничто на земле не проходит бесследно, и юность ушедшая тоже бессмертна. Yes, do you know this one? No? Тоже бессмертна. No. Okay, then no. No desire to listen to Russian music? Okay, then. So nonetheless, nevertheless, there are going to be a lot of applications of exponential distributions. So some physical phenomena such as radioactive decay, they exhibit memoryless property. And the exponential distribution is connected to other distributions. So for instance, to Poisson distributions, they have a shared story. And they are also building blocks for much more complicated distributions, such as Y-ball or V-ball, I'm not sure how you pronounce that, which model wear and tear effects, which are not memoryless, but nonetheless built out of exponential distributions. And that's for other topics, okay? Here is maybe one example about this distribution. So almost a true story, I would say. I have a friend, his name is Dave, and he used to be extremely tardy. So we often would take very long walks, and that might start near my place or near where he used to live. So let's say we schedule a meeting at 12. I knew that that the time it would take him to come out, let's say D is the amount of time it will take him to come out, it's exponentially distributed with parameter 1/10, right? And I would therefore implement what I called Dave time correction. Okay. In other words, you tell him to come out at a certain time. We agree to meet at 12. He would come whenever, right? It might be in an hour, who knows when, right? So when he would schedule to meet by his house at 12:10, my arrival time A would be uniformly distributed between 12 and 12:10. So I would come in 10 minutes, at most 10 minutes late, right? Somewhere between 12 and 12:10. And when he would swing by my house, let's say at some time t, I would come out to greet him at a time uniformly distributed over t plus and then t plus 10. So I would always basically meet him within 10 minutes when he's about to be there, right? So here are a few questions. Let's see if you can solve them. Given that Dave has been waiting for me for the past 6 minutes by my house, what is the probability that he will have to wait another 3 minutes? Do you understand? I come to greet him within a time distributed uniformly from the time the time he said he will arrive and 10 minutes later. So given that he is already waiting for me for 6 minutes, what's the probability that it will take me that you would have to wait another 3 minutes? Question clear? Enough? There you are, Sho. I thought I pressed to let you in, but I guess you were still waiting.
Yeah, sorry, I guess, yeah, waiting
Okay.
for a little bit.
It's fine. All right, so this question is hopefully A. If it's not, maybe I wrote it and maybe the question is not clear. I hope it is clear. So it's simple, right? So I go out to greet him with a uniform distribution. Good. So I will not make him wait because he's my friend more than 10 minutes. So if he's so let's say he is at my door at some time t, and then from that time I will come out to greet him uniformly at a uniformly distributed time between 0 and 10. Do you follow? So let's solve it here. So the question is here: what's the probability that Arkady will leave the house 3 + 6 minutes? Given that he is already, that Arkady hasn't, left for 6 minutes. That means he's waiting for me for 6 minutes. That's how I set it up. Good? It's all about me. when I'm the random variable. It's all about him when he is the random variable. So that means that I'm interested in the probability that I leave later than 9 minutes from his arrival, given that, or divided by the probability that I will leave later than 6 minutes after his arrival. Good. Now, what should that be? Was it 6 or second? What did I say there in my notes? 6 minutes. Yes. So, so this is what? So, what's the length of this interval? It's from 6 to 10. So its length is 4 divided by 10, right? That's the probability. The length of the interval, if it's uniform, divided by 10, 4 over 10. Are you with me? And this is 1 over 10. So the answer is 1/4. The probability that he will have to wait longer than additional 3 minutes is 1/4, 25%. Good. Now let's try to see the same situation in the other way around. So given that I was waiting for the past 10 minutes for Dave to come out of his house, what's the probability I will have to wait 10 or more additional minutes? Remember that he has an exponentially distributed random variable. He exits exponentially distributed with average of average of 1 over 10, right? So the probability that D is bigger than 10 is the integral from 10 to infinity of 1 over 10 e to the minus t divided by 10, right? That's the probability that, first of all, that he will live, it will take him to live longer than 10 minutes, right? Why do I don't need to consider anything else, because it's memoryless, right? So I don't need to worry about how much time I was already waiting, or maybe he doesn't worry about that time. For him, it's as if I just arrived. You understand the point? Do you see why I calculate probability D bigger than 10?
Is it because he had to wait? You have to wait longer than 10 minutes?
Well, so in B, I said suppose that that I waited for 10 minutes, right? So what's the probability I have to wait additional 10 minutes? That's the question I asked in B. Now you missed, Shotaro, you missed the introduction. Exponentials, they have a uniform distribution, right? Exponentials have a uniform distribution. So that means that whatever happened in the past, it doesn't matter. There is no, as I say uniform, I'm sorry, my brain is, I mean exponential random variables have this memoryless property, which means whatever happened in the past is not influencing. You see here I said, what's the probability Arkady will come 3 minutes, 3 plus 6 minutes after Dave arrived, given that Arkady hasn't come out within the first 6 minutes of arrival. And here the answer is 1/4. Uniform random variables are not memoryless. Good. But exponential random variables, the fact that 10 minutes elapsed doesn't matter. That's something I mentioned above where you missed it. So that is just simply the integral that I have to just that Dave will come out after 10 minutes or more from this very moment. So the fact that I already waited 10 minutes doesn't matter at all. The probability is immediately new. Okay, so if you were, here is what this is saying, guys. If your life expectancy was exponentially distributed, then a person that lived to be 100 years old, what's the probability that he will live 100 more years? The same probability as if you were just born. Do you understand? That's what exponential variables are like. So they are not affected by what already happened. Even if the probability of living to 100 isn't high, if you manage to live to 100, your probability of living further to 100 is not changed. You see, you can be 100 and it's as if you were just born. That's what it would mean if people had exponentially distributed lifespans. So the probability that d is bigger than 10 is the integral from 10 to infinity, 1 over 10 e to the minus t divided by 10. And it happens to be e to the minus 1, which is 0.37. Okay, so it's a higher probability that I will have to wait this duration. And then here is then annoyed. I complain to Dave that he is very inconsiderate. There above this accusation. So here above this accusation with this typically cynical smug. On average, we wait for each other the same amount of time, he says. When I visit you, it takes you an average of 5 minutes to come out, whereas when I tell you to meet me by my house at 12, you typically arrive 5 minutes late, and I exit my house on average at 12:10. So on average, we wait for one another the same amount of time. Who is right? You understand what I'm saying, guys? So how much do we wait for each other? Let's do it maybe. You want to try it on by yourself, or you want us to do it together? Okay, together. So do you agree that expected value of the amount of time he has to wait for me is 5 minutes? If he arrives at 12, I mean, once he arrived, it starts the uniform random variable. Do you understand? Once he is at my door, that's the idea. He calls me, I arrived, and then I begin getting ready and I come out. Good? I come out. I always implemented what you call it correction time. You understand? So if he would come by my house, he was already standing there. I see him out of the window. I said, okay, I'm coming out. And I start the random variable, the uniform random variable. So in other words, I will exit anytime between 0 and 10 minutes. And so on average, he will have to wait for me 5 minutes, because that's the expected value for the random variable distributed from 0 to 10. You just take 0 plus 10 and divide by 2. You remember that, right? We covered the expected value for uniform random variable, correct? So now what is the expected value for Dave? What's the expected value when Dave comes out? So his expected value when he comes out is t divided by 10 times e to the minus t over 10. Which I just again carry the calculation. I already knew it from before, but carrying that integral, I see that the expected value when he comes out after the moment we decide to meet. You understand? So the idea is this: when he tells me let's meet at 12 o'clock, I will implement correction time. I will arrive anywhere uniformly between 12 and 12:10. And he will exit uniformly. No, he would not exit uniformly. He would exit at an exponentially distributed random variable between 12 and and whatever time. Do you follow? So on average, he will exit 10 minutes away from 12. Okay, so on average, he comes out at 12:10. But on average, I arrive at 12:05. You understand? I arrive on 12:05. So on average, on average, the waiting time is what? So the waiting time is the expected value of d minus a, right? D minus a, it's 10 minus 5, where d minus a is how much I wait for him, because d minus a is since my arrival, how long do I have to wait for him? right? I don't always arrive at 12. I arrive uniformly between 12 and 12:10. That's the idea that I have here, right? And he exits at an exponentially distributed random variable between 12 and onwards with expected value equal to 10. Good. So on average, he waits for me just as long as I wait for him. Do you agree, therefore, that that we are in balance with one another? That he doesn't owe me anything and I don't owe him anything. That in terms of courtesy. So how many of you agree? Write in the comments. I'm not sure. Maybe you have no idea, right? How many of you have no idea? So write in the comments. I want to see what, or ask me questions if something is confusing or something you want me to re-explain. I'm trying to still get you home in time. So Naomi agrees, and who else agrees?
Wait, Professor, what's the difference between the expected value of D and then the expected value of the D minus A, like in this situation?
Because you see, if I were to be punctual and arrive at, let's say we agree to meet at 12, if I were to just arrive at 12, I would wait 10 minutes. So I decided to implement what I called, it's true, that's what I did, a Dave correction time, I called it, right? So I would come at a time uniformly distributed between 12 and 12:10. And that means that on average, I will come 5 minutes late. And on average, he will exit 10 minutes late. So on average, when I came to visit him, I would wait for him 5 minutes. You understand? That's what I'm saying here. Because I know how he would behave, I made it so that on average, I will wait for him 10 minutes. And then to punish him, when he came to visit me, I would also not hurry to visit, right? So what I would do is he's arrived, I see him under the window, and I'm still not prepared. So I'll just begin the correction time, and I will exit between 12 and 12:10. Do you follow what I do? So on average, he waits for me below my window 5 minutes, because on average, I will come out 5 minutes late. So on average, he claims, on average, we wait for each other the same amount of time. And we just calculated it here. So D minus A is how much he waits for me. So if A happened before, so if I arrived before D, D minus A is how much we wait for each other. Good. And I calculated the expected value of it. D minus A, by the way, could be negative, obviously, right? It could be that he gets out before me and he waits for me and I still haven't arrived. It could be potentially negative. Good? But the expected value of it is 5. So the expected value is that it is positive. It means on average, he will come 5 minutes after me. So what are your thoughts? So now Naomi doesn't agree, I see. Yes, it's good. You know, you should take my side. I'm giving you the grade. All right, let's look at it together then. But you have no feeling about it, or what goes in your mind, guys? Confusion. You can write confusion if that's what goes in your mind. But what happens there? Okay, confusion. That's something. And what about the rest of you? Okay, so interpret doesn't care for the minutes. Well, there is this very good song you should know. Do not think of seconds from above. Moments will pass by you and you will understand they fly like bullets across your temple. Moments. Do you know what it is? No. See, I need to show you so many good things. So here is what we can say here. So on average, he waits just as long as I wait for him. However, the probability that he will need to wait for me longer than 10 minutes, it's the probability P, let's say when he comes to visit me, right? It's the probability PA bigger than 10, which is 0. In other words, he never has to wait for me longer than 10 minutes. You agree? Because so whereas the probability that I wait longer than 10 minutes is the probability that D minus A is bigger than 10, which is the probability that D is bigger than A plus 10, which is an integration of Calc 3, right? So it's the integral from 0 to 10, probability of D bigger than A plus 10, times 1 over 10 dA, right? Because they are independent of one another. So it means that that D is bigger than, you can construct such distribution, right? So that would be integral from 0 to 10, 1 over 10. Do you understand how to set up this integral, guys? Yes? I'm just interested in the probability that D is bigger than A plus 10. So what does it mean? It means that if A if A is equal to little a, then D is bigger than A plus 10 if D is from A plus 10 to infinity, right? And what I have is the density functions 1 over 10 e to the minus t over 10 dt dA, right? So that I just integrate this situation. You can think about Riemann sums, or it's pretty quick. Then you can come up with this idea. If you need a review on it, I will show you. So it's the integral where a goes from 0 to 10, and given a particular a, the integral from a plus 10 to infinity of 1 over 10 e to the minus t over 10 dt will represent, for that particular a, what's the probability that d comes 10 minutes after this a or longer, right? So that's for what I do is I have a Bayes formula here. For any particular a when I arrive, I consider the probability that that he exits at least 10 minutes later. You understand? And I just go over each particular a. And when I carry out this calculation, I see that it's 0.23, which means that he never has to wait for me longer than 10 minutes, but with probability of more than 20%, I have to wait for him longer than 10 minutes. So it's not the same, you see? I experience very long durations. I might experience, you understand? So it's not just 10 minutes. I might experience half an hour delayed. It's not a zero probability that I will wait for him half an hour or 1 hour, as in fact happened many times. The longest record I waited for him was, I think, an hour and a half. Good? Do you want me to explain this integration, or you don't, by now you kind of already, doesn't matter? If you want, again, for me to go over this integral, I can explain how this is set up. You know how to do double integrals here. I should hope so. Okay. He, by the way, never remembers my birthday, this piece of... All right. I remember his birthday. By the way, you know, my grandfather, when he died, I thought it's going to be his birthday. Exactly, right? The death of my grandfather is exactly on his birthday now. Yes. So that ends this lecture on exponential random variables. So what's left is joint distributions. There is this lecture note, which is 11 pages long. And there is one more lecture that independent random variables there. So what would you like to do? Would you like to read it? Would you like to cover it? Would you like to not be bothered by it now? Message. I'm asking simple, guys. Do you want me to go over it or you prefer not to? Okay, good. I don't see a huge enthusiasm. Like, please go over it. So it means to me, are we going to meet on Wednesday? Do you want to meet on Wednesday? Let's ask this. We can continue this lecture on Wednesday. Do you want to meet on Wednesday, or you had enough of me? It's not. You're not at the dentist. It's a simple question. All right. So I suppose it means you want to do it on Wednesday. All right. So then let's continue on Wednesday. Fine with me. Goodbye then.
Professor, I have a
Yeah.
question of one of the questions on exam 2.
Yes.
Just
Yes.
to
Of course. Of course.
just to clarify the question on it's question 9.
Okay. Let's look at it. 1 second. And the other questions, they make sense to you?
Well, I'm trying to get through them. Yeah, question number 9. I just need to.
All right.
So how many? So
It's expected value problem. You have a similar question in my lecture notes. So so here you see what you have is you select n words. N is, it could be 20, 30, 50, 100, I don't know, right? There's going to be a sentence built up of randomly chosen, let's say 100 words. Each time you make a choice, it's one of the words mortal, coil, this, shuffle, off, to be, not, or whatnot, right? So those are the words that are going to be placed next to each other. The question is, on average, what's the expected value? How many times do you expect the sentence to be or not to be to appear? You follow? So the sentence could be something like this, you see? So if I see something like this, to be or not to be or not to be. how many times do you see in this sentence? How many times do you see the word to be or not to be? The full sentence to be or not to be?
Like twice.
Twice, exactly, right? Because you have
Okay.
although you have overlaps, but here to be or not to be, and here the other overlap.
Oh, okay. Yeah, that okay. I was reading the question wrong. Okay.
You understand? So the question
Yeah.
is expected value. What's the expected value of this thing?
So the amount of n doesn't matter, just like for however long. It's like how many would you expect?
Yes. N.
Okay.
Well, n is of course n matters because you see how many in this case. What is my n? Let's say if I only run it to be this long, it's the n is 1, 2, 3, 4, 5, 6, 7, 8, 9. You understand, right? N is how many words are you generating? So n, of
So
course, if I generate lots of words, then I might have more chances to get the sentence. So the question is on how much do I expect? On average, how many times do I expect the sentence to be part of my sequence of words?
So if it's anything less than 5, we're not going to get, like, the expected value will be 0 then.
Yes,
Anything less than
if
6.
there are 6 letters, so of
6
course,
or
if,
less,
if
yeah.
n is less than 5, it's 0. And of course, if n is less than what? Then whatever number, the minimal number I need to get to, then it will be 1, of course, at most, right? Or maybe
Okay.
less. It could be a fraction. Do you understand? It can be a fraction because the probability affects averages.
Okay. Yeah.
Good.
Yeah, I understand the question now. So thank you.
I actually have a question about it now.
Okay, go
Because
ahead.
before, I think I was looking at it wrong before, because now that you explained it, it seems different. So can you think about it as if you're picking words with replacement? Or is it
Of
not
course, you're
really
picking
on
them with
that?
replacement. Each time you pick a word, you can pick it many times, as many times. The sentence could be b b b b b b b, right? But each time it's like a roll of the die. The die, or however many faces it has. Yes, it has actually 6, maybe more than that to have the possibilities of other.
And it's with
Words.
replacement because a couple of words repeating, right?
Of course.
So you
Yes,
just
so it has to be replacement, of course. So it just randomly, each time you have to generate a sentence involving, let's say, 50 words. If it's 50 words, then each time you generate a word, it's one of those. Maybe it's next word, one of those, next one of those. And the question is not the probability to generate this sentence, but how many will we generate on average if we play this game.
And do the words have to be in order, or you can shuffle around words to make the sentence?
I read left to right, so I can find them anyway. I can find something like shuffle, and then to be or on, right? So all that matters is that somewhere in the sentence I see a full string that reads to be or not to be.
Okay.
Good?
Yeah.
You like this question? I like this question very much. I don't know.
So basically, first we would calculate the probability of this string appearing.
I didn't say that. That's what you're saying.
Yeah. And then after
in
that,
other words, again, I am not saying that, right? So you might create yourself a lot of extra work that's not necessary at all. I'm telling you, calculate the expected value. How many times it appears, right? That's what I'm saying. I didn't tell you what to do first or second, right?
Do we need to know the probability of each occurring for expected value though inside the sum, or
probability of what occurring?
Like if you're to roll a dice, like the probability of 1 occurring or 2 occurring, or am I thinking of it completely
Well,
wrong?
I mean, you do have to know what can I say? I mean, to roll 2, right? So you have to decide how to calculate the expected value here. Each word can appear in each place independently of whatever else happened, right? It's 1 out of, let's say, the probability that this thing will be coil is, I think, 1 over how many words I suggested? There were like 9 words, nine words available, maybe 1 over 9 at this particular place. Is it 9? I haven't counted them. How many we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually,
Yeah, it's
exactly 9, right? So coil to be in the second place, the probability is 1 over 9. Now, to be or not to be in the first 6 places, it's 1 over 9 to the power of 6. Do you agree? Because they have to be just right. Each of them has to match exactly correctly. All right, I'll let him go, all right? He's not registered in this class.
And what about, oops.
Yes.
Delighted.
Yes, what about what?
So what about this painting that you sent?
Yes, well, you look at the picture and there is a final exam question, and if you,
Oh, at the final exam.
huh?
Oh, it's not for today?
It's for the final.
Okay.
It's what, when, where. Do you want to play a game of what, when, where to understand what the game is about? Have I played it with you? You want to play one round?
Now?
Yeah. All right.
Do you just need to know what, when, where?
Yes, you definitely want to know this. Well, you don't need to know the game. The question can be answered. I can show you what the game is about. It's a big. You miss a lot by not playing it, so to speak.
Wait, this so this painting question is for the final exam, yeah?
Yes.
It's like action kind of.
Yes. Do you want to see what the game is about, or you want to go?
I have to go, but thank you.
Okay, then goodbye.
I might email you with more questions later.
Okay.
Bye.
Oh, Professor, I have one more small question on the exam. I forgot it was like if it was question number 4 or number 5, but if it was like I was just wondering if like each choice was like looking at the problem, it didn't seem, I don't think they were independent. I think
Which question are you talking about?
I believe 4 or 5. Let me
Okay.
yeah, like I think this, like if so x would have to be between t and n.
Yes.
And my thing is that when we unwrap it and we find a ticket, each time we find it, with the probability pool of whatever we have later like change, like they're not completely independent.
Yes, of course it will change, but you're also of course it can change, because once you remove think about it, I mentioned at the beginning of the class that this particular problem is very similar to the problem on exam 1 about the transistors. It's the same situation, right? Instead of now the chocolate bars, the transistors are chocolate bars, and the broken transistors are the chocolate bars that have the ticket. It's the same. It's the same type of.
Oh, it's the one with the replacement. Yeah.
Yes, it's that. Remember?
Yeah, I remember that. I forgot if I got it right.
Yes, well, you can check, right? And so it's a similar problem. And what you want to know here is you want to find the probability for x, and you want to calculate expected value.
Find probability for each like x, and like so find the formula. Okay. And yeah. Oh, number 4, the transistor one. Yeah, for that one, I think I got it so wrong that even you were confused by it, my understanding of it. Could you go over that
problem? You want me to go over that transistor problem?
Yeah.
Okay. So here. Oh, here it is. It's problem number 4. Good. So what happens here, right? So because the transistors are the same, I mean, I suppose I would have done it this way. So the transistors are all the same, and the Kafka protocol then that I would build is, well, okay, take care, interpret. So I imagine that they are all the same, and they're put their places. Place 1, that's the first transistor, second transistor, third transistor that I check, right? All the way to the 12th transistor, okay? And I check. Some of them are let's say whenever I find the broken transistor, I write 1. Otherwise, I put 0 in my form. Okay, so what those are just spaces, right? Then I can imagine in my form, this is the actual maybe actually those are the actual transistors that I investigate. Okay, and so on my form I can report how I find those transistors. So in general, which spaces occupy the broken transistor? There are 3 of them. So in general, there are 12. Choose 3 possibilities. Do you agree? For the broken transistors. You understand? But 12 choose 3 is basically it's out of the places 1, 2, 3, etc., all the way to 12. Which of those places occupy the broken transistor?
Yeah, so whichever one's broken, you
yes,
have
and
3
then
to choose
you
from.
can
Yeah.
solve it in many ways. I can show you many possibilities. So one of them is, suppose that you were able to. So suppose that. What's the probability the inspector will have to test 9 or more transistors, right? So the testing is going first, second, third. You go and test in this order because you cannot tell them. There's no reason to do it otherwise, right? So
I think
the first transistor tested, second, third, fourth, etc. Right?
Yeah.
You can think of this as happening in this particular sequence. Good.
Yeah.
So what's the probability that that you have to inspect more than 9 transistors? Well, that the biggest of the numbers, we can do it this way. The biggest of the numbers tested is 9, or the biggest is 10, or the biggest is 11, or the biggest is 12. Okay, the last transistor that I checked. Then I checked more than 9. That's one way to do it. Right. So if the biggest is 9, then I have 8. Choose 2. That means biggest is 9, right? The last transistor I find is 9, and that means I had to test 9 or more transistors, right? And the remaining ones were in the first 8 boxes, right? The remaining 2, I found them before. So that means the last transistor was found in position 9. Plus 9 choose 2 means the last transistor was found in position 10. Plus 10 choose 2. That means the last transistor was found in position 11. Plus 11 choose 2. That means that the transistor was found in position 12. So that's one, maybe the simplest way to do it. Maybe not. I had several ways of doing it.
Yeah, that makes because so you're essentially like selecting all the options that would be for the other 2.
Yeah, so that should give you a good hint on what to do for that problem you're wondering about. Because I stopped collecting the Wonkas once I found the last ticket. Same thing. You agree? So there you said we have x that's equal to t or all the way to n, right? So the question is, what's the probability that x equal to k, where k is a number between t and n? And if x is equal to k, that means that I found my last Wonka bar, my last Wonka ticket at the very last, at the position number what? I found Wonka at position number.
Yeah, so like you can, so the biggest would be you'll find on the nth one.
Well,
So that
if x is equal to k, let me just clear it. You all have this thing, you understand, right?
yeah.
So back to that other exam, the exam number, was it exam number 2? Yeah.
Yeah, it was number 2.
Yeah. So it was which question? It was
Number 4.
also number 4. What do you know? Was that before
The
number 4?
coincidence.
Coincidence.
Yeah.
So what is this question? Look at it. So what's the probability? I'm not gonna fully write it, but think about it. So what's the probability that x equal to k, which means that I sampled all the way up to k, right? So because I continue, that x is the number of Wonka bars opened. How many I opened until I have found all the T golden tickets? It means that I opened k and I found all the golden tickets, right? Which means what? It means that that the last golden ticket was found on which bar? On which bar number?
On bar number k, right?
Exactly. Because why would I continue? I continue opening until I found the last bar. I know how many tickets I should find already. I don't know where they will be, but I know how many tickets I should find. So
and then we find the probability for like the formula for essentially t between t and n, and then we put that into the
well,
expected value
but the distribution is this because it's distribution. Find the mass function for x, which means you want to know what it is for just a generic k, where k is either t or t plus 1 or all the way to n, right? Because you said yourself, I have to open at least the first. I have to open at least t, right? So how many did I open?
Yeah.
Right. So you understand, because they are identical. I pretty much I can say first I opened, and that will be first round. Second I opened the second. You understand? I can imagine that those are like curtains, and I can imagine opening curtains in this direction because it doesn't matter, right? It's probabilistically any other procedure is just doing the same thing.
Yeah. Okay. And the problem mass function, the sum should equal 1, right?
Mm-hmm.
Of all of them.
The
Yeah.
sum should equal to 1, but you don't have to investigate it. Like, I mean, if you want to, you can try, but it's clear that I will either have to gather t or t plus 1 or all the way to n, right? So
Yeah.
it's somewhat, yes, you can prove it if you have to, but the question is to find this and to find the expected value, to find the mass function, right? So what is this, right? So what you understand what the mass function is? Yes, Shotaro?
I believe so. It's which area like the probability is located. Like it's like a graph.
Well, that's the density function. The mass function is if it's discrete, it's like we have all those possibilities in the sample space, and how likely is this? So this is one outcome. This is another outcome. How likely is this outcome? So how likely is the outcome to be x equal to k? So the outcomes here are t plus 1, all the way to n, right? What's the likelihood it will be n? You understand? Just the probability that x is equal to k. In other words, probability that I had to open t, the probability I had to open t plus 1. So in general, the probability x equal to some k. I can specify it in terms of k. It's going to be different depending on how many I open, right? It might be one probability that I opened exactly t, probably a little bit more likely I opened t plus 1 or t plus 2, a little bit, because it's likely that I missed some, right? It's more likely than I just opened all of them. And one after the other, I was successful. But so you just calculate the probability. Does it make sense, Shotaro?
Yeah, it makes sense.
Okay. Anything else I can help you with, guys?
We have to submit exam by Wednesday night.
Yes. If it's extremely problematic, you can take a little bit longer time, but it's just I have to grade both this and the final, right? The final has to be done by the weekend, by the end of the weekend, because I have to grade it very quickly.
Okay. Thank you, Professor.
Thank you, Professor.
How far are you away from solving all of it? Far? If you need some help, I mean, I can try to help. What else can I do?
I think I'm pretty, like, not close, but I think I just need to go at it more. I think I'm pretty confident through one through 3 I did, and then I think I did number 8.
Mm-hmm.
And 4 I just got the hint on, so you know, I think I should be able to get it done by Wednesday.
Right. All right.
All right. Thank you, Professor.
Take care, guys.